Welcome. We are glad that you're here and participating in the KidWind Design Challenge. My name is Sue Tenney. The emails have been coming from me to this point. But Susan, do you want to say hello since you're kind of managing this challenge?
Did. Hi, I'm Susan. I'm from OEP. I'm a retired high school physical science and ecology and biology teacher. I've been with OEP. I was one of you guys. I did some workshops with my students. So I'm on the other side of the table now. And I built one of the KidWind things. So
she was our R&D person. So
you're in good hands with her.
Yeah. So you are welcome to, when you start with the project, if you have questions, you are welcome to email them to me. I will be forwarding them to Susan though. So just so you know that one of us will get back to you. All right. So I think Mike from KidWind, we're going to let him kind of take it away. He's going to walk you through what is in the box, some putting together things. He's going to talk a little bit about the online portal. Hey, Christy Carter, that just walked away from your computer. So this is super low key and informal. I will keep my eye on the chat. So if you have questions, you can either put them in the chat or you can just unmute yourself and ask as we go along. So whatever works the best for you all and what you feel comfortable with. So Mike from KidWind, take it away.
Hi, everybody. Nice to meet you. Hopefully you've gotten a box for me at some point of stuff, hopefully. My goal today is just to maybe orient you a little bit to the box if you haven't taken a look at any of the materials and sort of some of the setup. Show you a sample of an online portal that you will be using to sort of compete online, I guess, best way to put it, and sort of what data points to put in. In addition to one part I'd like to show teachers, I notice you're all high school teachers, so sometimes you're all really smart about this, is collecting your voltage and power data under a resistor tends to be the bottleneck for a lot of these things. So I want to show you a little bit about that too. And if you have any other questions you really want to know, you can throw them into the chat and I will try to deal with those because I'm right here. I have gone through the website that OEP set up for you guys, and it has a lot of really nice resources. I think Susan must have set that up, and it has some great resources about how to teach wind and how to do some of the kits and stuff like that. So you've got a great resource there. But after this event, you can definitely reach out to me at any point to help as well. I like to try to help these sites. This is kind of one of the more ambitious online state level challenges with 70 or 80 teachers doing it. So you guys are really going after it. So with that, I'll let anybody throw questions in there, and Sue and Susan can let me know. But you got a box of stuff, and it was probably pretty obvious to you. You got some parts there to make a tower. Okay. The one thing I will say is there's this little ring part. I'll show you that there. That fits on your tower. It can be a little hard to get that on there. If it's on there like that, I tend to kind of like, if it's not really fitting, put it inside to this device, kind of like here, and just kind of pound on it as hard as you can. This stuff is like pretty robust. You could hit it with hard things and it will survive, okay? But that is one trick with the tower, is that ring sort of fits on the tower there, and you kind of put it in there and do that. The legs just, snap on, pretty simple. I will say, when the kids are testing your turbines, for those of you who've never done this before, sometimes it can be nice to put some weights on the bottom here, because if they make large blades and the fans hit it, it can kind of tilt and things like that. And I will say, when kids are sort of testing blades around the turbines, I tended to have them with safety goggles on of some kind. When they're making their blades and stuff, I tend not to worry too much about it. But when they're near the turbines and they're spinning around and stuff like that, it can be a good area to make sure your kids sort of have their goggles on, good science, safety protocols and the whatnot. So that's your tower, okay? If you've got some of you got like 2 in one box, some of you got like 1 in one box. You also probably got some PVC parts that look kind of like this. You got a T and a coupler and a short piece of pipe, okay? And this part is designed to sort of, the fancy word on a wind turbine is this is your nacelle. A nacelle is a fancy word for where all the stuff is in a wind turbine, okay? And that sort of fits on the top of your turbine, okay? Like this, kind of. We'll get there eventually. But that fits on the top. And you got this part. So now what you got to do is you got to take your generator. It's got some wires attached, okay? I got some people in here. Hold on a second, guys. This is probably the most, I don't know, the hardest part of this, but it's not that hard. There's 2 ways you can do this. You can snake your wires so they kind of go down the T. Got dogs here walking around and barking. Sorry, guys. If you do this, where the wires come down through the T, you can then snake them down your tower. But if you do that, you'll notice there's no hole in the bottom here. So if you do that, you'd want to like drill a hole in the bottom of your thing, okay, and then run the wires out your tower. You don't have to do that because you could just do this if you didn't have a drill. Is just snake the wires out the back of the T. Okay. I'm curious how many people have ever done a KidWind stuff in their classrooms too. If you have done it before, we'd love to know. But now I've got this wire running out the back, so now I don't have to worry about drilling holes in the tower, okay? And when you do put this on the tower and you run the wires down, it can be a good idea to tape maybe your wires to the tower, just keep them out of the way so kids don't yank them and stuff. It's not a bad habit to get into. But now you've got this generator, and all this really is, this generator is a DC motor. And we've tested a lot, so this one works well for this application. But a DC motor, basically, we can put electricity in and it spins, or we can spin it and get electricity out. What we like about this DC motor is that when we spin it, we get decently measurable voltage output. So it's not just like spinning and we're not getting any data, okay? So that's the part we like about this a lot. But you're gonna notice you're gonna put it in here and it's gonna be like, it's loose, okay? So the way we deal with that is you take a piece of duct tape that you've kind of stripped in half, and you're gonna wrap it around the outside of the motor. Okay. And it's about 18 inches or so, depending on how thick your duct tape is. Okay. And you wrap it around the outside of the motor. And now when you put it back in here, it should be tighter. Now mine is still, and you can kind of see here, it's still a little bit loose. Okay. So I'd probably want to put more tape. And what you don't want to have is, this is where the kids are kind of pressing a lot. If it kind of pushes in like that too far, you probably want more tape, okay? You want more tape. You'd rather have it be so tight that like it's a little bit sticking out, okay? I tend to say too, once you get to this point, it can be a good idea once you get it to really close tightness, put some hot glue around there, or some epoxy, push it in and let it get set. Then you'll know it's like not gonna go anywhere, okay? But you do wanna make sure that part is very tight when you're working on it, okay? Any questions about that?
When I made mine, I came out the back and I just wrapped it around and then taped it on the bottom.
That's a good idea.
And then as far as putting things in the nacelle, it's pretty long and you would really have to stuff it all the way in. I think the tape and the hot glue are really the best ideas.
Yeah. And this, you're making a really, we'll call it a poor man's turbine in some respects too. It just works. This is like the original version of a KidWind turbine. But just fiddling with the amount of tape and getting it to the right spot, you'll get in a good place where it's like nice and tight.
It'll be nice and snug. It'll work.
Yeah, it'll work for you. Okay, so once you get to this point, you got yourself a turbine. You're like super excited because you got a thing that functions. once again, has anybody ever done like blade stuff in the classroom with their kids you can throw it in the chat if you have. Just curious if any of you had. The next part is sort of where all the inquiry comes from and all the engineering. It's kind of, we got this turbine, but now we got to like figure out how to optimize the power output. And for this device, you know, the area we can sort of work on a lot is this blade area too. And in your box, you got a bunch of these. These are called hubs, okay? And these are what allow us to attach the blades. And this is designed to just press right onto that shaft, okay? So when you get to that point, this sort of presses right onto the shaft there, and then it sort of rotates. But that's the sort of space we're gonna live in a little bit, is that the blades, sort of how do the blades work, how do they function, and things like that. And anybody here in the chat, if you want to throw it in the chat, if you can think of all the variables that your students might come up with blades, what do you think they might be? Because there are quite a few that you're going to find your kids doing as they start to unpack this a little bit and do some things. So feel free to throw in the chat, like, what are some things about the blades that can vary quite a bit? You got number of blades for sure is going to be one the kids definitely mess with. Other things, shape. So yeah, you're going to get lots of different shapes, squares, circles, all sorts of stuff. Angle or pitch, as we call it. That's like how it and you have in your box there a yellow device that allows you to measure pitch. And I should actually send a link to a video that Susan can put on the website that shows you how to do the pitch measurement. It's really handy. It's a really hard thing for me to show you, but it basically controls the pitch. Materials, another one for sure. So there's all these variables. You know, I will say as a hint right now, pitch is really important. Other things matter, but pitch, your kids are gonna start to determine is very, very important. Okay. And there's things like balance. If your kids make blades that are out of balance, it's going to shake the turbine and do all sorts of stuff too, okay? When you're making blades in your box, just grab stuff here. You've got a bag of dowels, okay? The way these work is kind of unscrew this hub a little bit. And it's pretty tight, so you can use this as almost like a pry bar, and you put it in there, and then when you get your blade in, you kind of tighten it down, and it kind of grabs the dowel, holds it in place. In the old days, we used to use Tinker Toys, but they didn't work well because as soon as it started to spin fast, they'd fly out. So this is like a modified Tinker Toy. So that hub just opens up a little bit, and then you make it tight, and it kind of eats down. But how you attach the dowel to the blades is pretty simple. The blade material we've given you is just it's just this stuff. It's like cereal board or something like that. It's like, you know, kind of thickish paper, thickish cardstock. Okay, you can cut it into any shape. You can do all sorts of stuff with it. Other things you can use as blades, because there's no rules against other things, but paper plates are really good and cheap. I know they're an environmental like catastrophe, but styrofoam plates are like the greatest blade making material on the planet. Reasons being that they are super light and super stiff. That's kind of what wind turbine blades are. They're super light and super stiff. So that kind of stuff is great. If you get really fancy, you can start to get into balsa wood. This stuff is very expensive. When I used to do stuff with my students on this space, they'd have to prove to me they knew stuff with like cardboard and other stuff, and then I would allocate some balsa to them as like a prize for being good at what they're doing. So, you know, balsa is very expensive, but you can use that too. That's actually what's in real wind turbine blades. Real wind turbine blades are actually airfoils that are made out of balsa and fiberglass in a lot of ways. If you get really sophisticated, this is a 3D printed blade. We see this a lot at national level KidWind challenges and some kids who've done this for multiple years. But this is 3D printed airfoil shape, that kind of stuff. But that's, you know, way down the line if you had a lot of time and a lot of equipment, okay? Cardboard works pretty great as a starting kind of process, okay? So keep that in mind. One other thing to consider too as you're designing your blades is if you're using a fan, you probably don't want your blades bigger than the fan. It's one thing to consider. Outside we've got a huge amount of wind, but in a classroom situation, we're really limited by the size of that fan. And kids will make things bigger than the fan, but anything bigger than the fan is going to be drag because it's not getting hit by wind at all. Okay, so keep that in mind. You could stack 4 fans together. I've seen teachers do that to make a bigger wind stream. That could be kind of fun. But keep in mind that that's one of the limitations of being inside. When you make your blades, whatever your material you use, you could just use duct tape, but I will recommend you use hot glue to attach that dowel to your whatever blade material you've got. The reason being is if you just use tape, you tend to get a lot of like motion of the material around the dowel and it sort of messes things up. So I really recommend hot glue as you sort of make your blades, however you're going to do it. Okay. And I know that hot glue in students is a nightmare. I used to allocate and you'd have to pay me for more because I was mean teacher when I did that, but it definitely works a lot better. So you got a turbine, you know how to make blades. Okay, you know that there's all these variables related to the blades that can get really messy. And we didn't even really talk about another area that can get really messy. This is maybe in years 3 and 4, Sue and Susan will go advanced. You can't even get into things with like gearing and stuff like that. This is kind of a large competition that you're trying to roll out. We're using direct drive as a nice place to start, to be very honest with you. It's a nice place to sort of go. Know that you can get really complex with gearing and all sorts of other stuff as well too, which really adds layers of complexity. But I would say for a first time around not dealing with that, sometimes it's okay to go that path. So you've got all these things, you got blades, you got variables. I will just do a little bit of a quick, when we teach kids how to do blade stuff, one lesson plan we do sometimes is we break kids into groups and we sort of say, okay, each group has to pick a variable they're going to test. And that could be some of the ones you've got in there, like length, pitch, number, shape. And what they do is then they're like lab group, they collect a little bit of data, and that's just like, number of blade versus voltage. So at 2 blades, I had this many volts. At 4 blades, I had this many volts. At 6 blades, I had this many volts. Like a little bit of a, inquiry experiment, basically. And each group's maybe collecting data on a different variable. And then we do that for a period and a half. And then we kind of share out, what did we find out about each of these variables? And then after that, we have all this data around the classroom. Hopefully, maybe some of the kids are reading it. Maybe some of them are not. Now you have to make the best set of blades you can. Okay, like look at that data and then try to build the best set you can. That's kind of the open-ended challenge. Some teachers do not do that data collection process. That is okay. But then the kids are sort of having to hunt and peck a little bit about what things are impacting output. But if you can sort of set them up with some of those dynamics, you kind of put them in a little better spot, if you get my meaning. So that, and some of the lessons I know Susan has set up there and some of the lessons on the WindWise site, we walk kids through that process a little bit of collecting some data. Now it's wide open, okay? But the one part that is pretty hard and pretty important is you've got in your kits a multimeter. By raising your hand by like, thumbs down, thumbs up, how many of you feel really comfortable using a multimeter? I see 1 thumbs up, thumb in the middle, thumb up. This is good. Thumb in the middle. All right. Thumb in the middle. All right. We got some thumbs. No thumbs totally down. That's good. I'm going to that. In your kit, you've got a meter. It doesn't look exactly like this, but it looks somewhat similar to this. Okay. For these turbines, you're going to want to set it on DC voltage. Okay. And the range, this is an auto ranging. So this is a meter that makes me set the range. Set it in the range of 0 to 20 DC volts. That's going to give you a nice range. A direct drive turbine like this, if you go anywhere above like 3 volts, man, you're crushing it. You're doing like great. Like a lot of kids are going to be 0.5 volt, 0.75. Ungeared, it's hard to get above 3 or 4 volts because you got to really be flying. So you've got this, you got it in DC volts, and in your kits, you should have had a piece of paper that had a resistor attached to it, okay? Turns out the best resistance for this turbine is 30 ohms, or that generator is 30 ohms. That's why we've given you a 30 ohm resistor, all right? One thing you're gonna wanna do as you record, and I'm gonna show this in the where you upload your data, okay, in a second, but we could just like attach cord here. We could just attach, and I'm basically taking a clip cord and attaching my black wire to my to one lead of my multimeter and the red wire to it too. So now my turbine is connected, and it should, if I spin it. So now if I spin it there, you'll see some numbers. That's what we're really looking for. That's like, quantitative data. Okay, that's the thing we're looking for. But right now, the way I have it hooked up to this, and I can try to show this, is each wire is just connected, and I'm measuring the voltage between the two wires, okay? There's no load on this turbine right now. Basically, it's just like free spinning, okay? There's no load. It's not having to do any work, okay? The reason we give you a resistor is it then forces this turbine to do work. And I'm gonna try to show this. There are some nice diagrams in the stuff that Susan has put on the website for you guys that is a lot easier to see than what I'm gonna do here in this format. But what I'm doing now is basically if I measured the voltage on these leads, but I have, and I'm trying to do this here best I can. I'm wrapping each lead around the resistor. And you can kind of see, so now you see like the red and black leads are on each side of the resistor. What's happening now is we know electricity travels in a loop. It's coming down one wire, going through the resistor, and then back through the other wire. We've created a circuit, but in the circuit, I now have this resistor, okay? This resistor is like kind of like a miniature toaster. It's gonna slow the flow of the electrons, okay? Now what I wanna do, and this is gonna be the really hard part because I don't have 4 hands, but I will try my best, is now I want to measure the voltage at each of these leads. I'd have, one on this side and one on the other, and then I measure the voltage. And this is the way the terminology we use for this is measuring voltage under load. Okay, under load. We're measuring the voltage between the wires, but it has a load on it. Okay, and that is the one tricky part. Some kids or teachers don't do this, and the data you get is okay, but we can't really calculate your power or energy output if we don't have you under a load, okay? And like I said, there are some very nice like diagrams that show this that are way better than me holding things up in front of cameras. But I want to show you kind of just the basics of this right here. And what you will notice as you do these recordings is under load, your voltage will go down. Like let's pretend your KidWind turbine was making 1.5 volts. As soon as you add a load, it might drop to 0.5. That's what's going to happen under load, okay? So that's just what's going to happen. We, in some of like KidWind challenges where kids come together in groups, we'll have kids that come in and they'll be like, I'll be talking to them as they get ready to put their wind turbines in a wind tunnel. And maybe after the pandemic, we can come to Ohio and do an actual like in-person KidWind challenge. That'd be a lot of fun. You guys will be experts then. They tell me like, Mr. Arkwood, my turbine was making like 13 volts before I got here. I was like, wow, that's great. And then I hook up their turbine to the testing apparatus that has a load on it, and it makes about 3 volts. And they're like, what happened? And they're in tears because they were making so much. And it's because they were testing without a load. So I don't want you to do that to your kids. It's kind of sad and depressing. So that under load is important. Any question? That's kind of hard to see there, but any questions about that? And like I said, Susan has a lot of great links. There's a lot of great videos that I can share too that walk through that in a little cleaner format too. You'll notice in your kits, you've gotten 10 of these hubs and 1 tower. The way we typically set this up in a classroom is we have a fan about 1 meter from the turbine. We try to center the fan in the center of the turbine, okay, about 1 meter away, all right? And then we kind of set everything up, and then the kids are working at their tables with these hubs and they're putting their blades in. And all they really do is they come up to the testing station, put their, hub in here, mine's a little loose, and they test, and they get a voltage reading, and they're like, get a number. And it's kind of nice for 1 setup in your classroom or 2. If you have it all set up ahead of time and the meter's there and the load is attached, they're really just kind of like putting their blades on, walking away, getting a number, and they can do that kind of quickly, okay? So that's really where the kids are sort of, the kids are really focused on this part and then this part and connecting these and trying to collect the data, okay? Any questions there? I always say you should pause for long instances on Zoom meetings so people can have a time.
If you don't want to type it into the chat, you can just
Yell it out
unmute
too.
and
Yeah,
ask
yell it out.
too. This seems like a good time. It might answer some questions. Or Mike, you're just doing such a great job. Everyone gets it.
Or it's 3 and you're really tired because you had a super long day trying to train crazy kids on a day after a 3-day vacation, which I totally have been there. I know where you're at.
That could be too.
Okay. I'm going to do a screen share if I can. I'm not sure. Let's see if I can. Okay, great.
You should be able to.
Yep, I can. Let's see if I can do this. Okay. So, oops, there we go. Hopefully you're seeing, are you seeing like a web page, hopefully, that says like November 2020? Okay, great.
Yes.
So this is a sample portal we use with teachers we do workshops at where they learn how to use the online platform, okay? My favorite is this one here where Bill Nye came to the KidWind booth and was asking us lots of questions. That's like 15 years old. I think that's super hilarious. Nowadays, but you can see like this is the page where you can see all the projects that have been entered, okay? In the first page here, you're gonna see project guidelines. Sue's going to set this up and Susan will set up this portal for Ohio and it will have a lot of materials and things. Although the thing that you guys have, she has a nice website that's all set up that has a lot of information. So a lot of this will probably just be a little bit basic here because you guys already have a website where you've got a lot of the detailed information going on, okay? This is the real meat of where you're going to be like, after your kids sort of collect all that data in their classroom, where do they put it so they can share it with the world? And it's under this submit your project, okay? And in here, you're going to see some things like team name. Okay, that's pretty easy. A project image. You should have maybe, I would say for a thing like this where the kids are working on their blades, this project image might just be the blades or the type of blades that are being tested at this time. They could have a description, okay, of their project and things like that. And I would say you'd probably do this uploading with like your final best set. You know what I mean? After you've done all your testing and you feel really good, okay, our final best set is now here. You could upload a research statement. The fields that you'll see here are actually, they're more determined by what Sue and Susan want to put in here. So they may be a little different than what I have here, but know that there's an option for like a research statement. Kids could write a report, things like that. The meat of the turbine performance is what I really want to show you. This is sort of the part that gets a little sticky. So the first thing you have to tell us to calculate how much power or power your turbine is making is, I need to know how fast your wind speed is. Now, you probably don't have an anemometer, okay? So we have a cheat sheet here. We made a poor intern measure wind speeds on lots of different types of fans and the distance from the fans. So if you said, I have this box fan and I'm 100 centimeters or a meter away, it's probably about that fast. I will say on Amazon, they sell anemometers for classrooms for like $20. So if you want to get an anemometer, they're out there and they're pretty handy. There's lots of different kinds and styles, but if you don't do that, this will get you pretty close, okay? So first you got to give us wind speed, and I'm just going to pretend most classroom wind speeds are like 4 meters per second, okay? Next thing you got to do is you got to do some math. What's your rotor swept area in centimeters squared? The units are important. You can make, being good science teachers, you can harass your kids to make sure they're using the right units. We even give them a little calculation guide about if they have horizontal axis or vertical axis. The vertical axis is a little tricky to determine, okay? So, but know that that's in there. I'm going to pretend I have something with like 1,000 square centimeters, okay? The resistor I've given you, that's 30, okay? The last thing is the voltage. So now we've got to figure out, okay, let's pretend Mike's turbine, I'm really smart. I made 2.5 volts on my direct drive turbine. what pops up at the bottom there, you're now going to see is based on those 4 factors you've given me, I now can tell how much power your turbine was making and the efficiency. The efficiency is a calculation basically, if I know a rotor diameter and I know how fast the wind is moving through that rotor diameter, I can calculate the maximum amount of power that's available in that disc, okay? And with the resistor value and the voltage, I can calculate the actual power you're making. So now I can compare your actual power to the theoretical maximum, and I can get an efficiency. And I will tell you, if your kids are getting, with a direct drive system like this, above, we call it the 5% club. If you're above 5%, you're doing okay. You're doing pretty good. The theoretical maximum, if your kids try to hack the system and do something like, well, I'm really smart and I got 10. The maximum efficiency of a wind turbine is 59%, as sort of described by the Betz limit. So this is like a theoretically impossible result, okay? So if your kids are putting data into the system and it's barking at them, tell them to go check their numbers because something is off, okay? And I am sure that Sue and the team that evaluates the turbines, one of the parts will be the power output, but there could be like, they may include other fields in here, like you can upload a video or a report or other things. So they're gonna probably evaluate them. I mean, we always look for a wide variety of factors. And I'm gonna stop my share here. If I can get my mouse back over here somewhere.
Hey, Mike, if I can add one thing. So if you are, when you do this, the student worksheet that Susan created to go with this, it has all of these fields on it that are required for the portal. So if you're using the student worksheet, you'll have, the students will have all that data that they need.
Yeah, and that's a good idea. Like it basically says like, once they finally collect that final data, then they can put that into the system and they've got it all in front of them and things like that. Typical areas where kids mess up, we see a lot of rotor swept area, math wrong, happens all the time. Like kids will be put in like, it'll be like 50 to 60,000 centimeters squared or some huge number, like it's a massively large turbine. And you just say, check your math, or they've got the units wrong. They've measured in meters and it's point something and not centimeters. So that's a common mistake. And then the resistor we've given you, and then the error sometimes is kids will be measuring their voltage, but it's not under load. So that's the other sort of mistake we see commonly too. But yeah, and like I said, the kids can sort of, they'll go crazy with this stuff. I mean, you'll see the blades the kids make, you know, they can sort of go as far as they want. We see like pop bottles, letter cut, and all manner of stuff. So you can sort of see a whole, we in fact make it one of the categories we do challenges, like, did you use like found materials, stuff found in the trash, stuff like that. So, you know, there's all sorts of ways to do it, but that's kind of a lot for after school day. So I don't know if you got any questions at all. And you know, I like I said, I know that Susan and Sue are there to help, but I hope that Susan, you know, you feel free to share my, I have done quite a few Zooms into classrooms, especially if you've got your kids building blades and you're in a classroom situation and you want to get like a hard critique from Mike. I have a lot of fun doing that, actually, like a half an hour jump into your classroom, like, why aren't my blades working well? I've done this so long, I can pretty much tell pretty quick, like where we can sort of go and improve things. The other thing that kids really mess up is pitch. Their pitches will be all over the place and it will cause all sorts of problems. So that's another thing to think about too.
Thanks, Mike. A couple other additional things on the portal, just kind of specific to Ohio. So a part of our typical summit program, but also a part of this program is a stipend for participating. So the requirements for receiving the stipend are, one, to complete a teacher evaluation, and we'll be sending out links to that. It's not complete yet. But then the second part is submitting at least one entry to the portal that Mike just showed you. And as I mentioned earlier, for Ohio, that's not quite set up. We'll have that ready to go here in the next week or so. So you'll be able to enter the data online. The requirement for the stipend is just one entry, but if you're doing this with multiple classes, or if you have kids that just really get excited about it, feel free to enter as many as you like. We will be giving away some prizes. Some of our funding partners for this program will be judging projects within their specific territory. So we'll definitely kind of give like a best efficiency award, but we're also, as Mike mentioned, there's a place where you can upload either pictures or a video. So we're gonna just give away some fun, creative best video and different
I have
things
lots
like
of ideas for fun prizes too, Sue. We do a lot of
Oh, we'll talk.
best constructed and all sorts of things. We do all sorts of funny things. So.
Yeah, so we want this, we recognize that this is a hard, impossible year to be a teacher. So however we can best support you, give you some opportunities for your students to have some different experiences, we want to be available. The other thing is this is our first time doing anything like this before. So if you have ideas, if you have questions, if you get in the classroom and logistically it's just not working, or if you need some additional resources from our website, please let us know. We're here to help you be successful with your students. So let us know what you need and we'll try and make it happen. Mike, thank you so much. Teachers,
Thank you, Mike.
Great work. Thank you for being a part of something new during an already crazy year. Let us know what you need and Susan or I or Mike will get back to you.
Yeah, happy to help in any way at all, anytime.
Have fun.
All right.
Thank you.
For participating.